All right, so welcome to lecture 2 of week 1. This will be a little bit of a long one since we only did the first section yesterday with the welcome material and everything. But yeah, FYI, a little business first. I changed the way the Zoom meetings are set up. So from now on, it's always going to be this Zoom meeting room. You don't have to worry about different Zoom codes for different days, so that'll be good. Also, too, it looks like Examity is all set up and ready to go. The exams have been imported over, so you should be able to get started on your account, get your ID uploaded, do your technology check, all that fun stuff. And then, yeah, I think you can also schedule when you want to take the exams. Like I said, you can do it last minute, but I think there's a slight fee for that, but might as well get it scheduled now so you know when you're planning on doing it. So I saw, okay, so our study group leader, Steven, is here. I don't know if he wants to pop in on camera and introduce himself.
Oh, is my camera not on right now?
I don't see you. I don't know.
Give me a minute. There you
are. Oh, there you are.
All right. Yeah, so thanks, Joe. So hi, everyone. My name is Steven, and I'll be the guided study group leader for this summer. So yeah, think of it as an extra aid every Thursdays at 4 p.m.
Yep.
I think we agreed on that. So we'll have an hour's worth of sessions every week on Thursdays. And what I normally do throughout my GSGs previously was I go over concepts, provide extra problems, and answer any questions you have.
Yeah, we'll have a spot on Piazza for that. I think I made it as one of the folders, GSG. So if you have something you want him to talk about, feel free to post that there.
All right, sounds good.
All righty, so yeah, thanks for popping in, Steven. I guess they'll see you on Thursday. I guess we could get into this material now. So yeah, like I said, this will be a pretty long one. Let's see here. So yeah, we're going to do 3 sections, 12-2 through 12-4. 12-2 is also sort of an introductory one. I think this really more so is stuff that most of you have probably seen. Yesterday with the 3-dimensional coordinate systems, we also talked a lot about dimensionality and equations and context. I think that stuff is really important. But for 12-2, I think that most of you already have been dealing with vectors in other courses, so this is really just a chance for us to make sure we're on the same page with notation and terminology and things like that. So yeah, first thing to understand is basically what is a vector. And I think the idea with a vector is it's not a good old regular number. So that's what I would refer to as a scalar quantity, is just a regular number. So certain scalar quantities are things like distance, speed, time, temperature, height, weight, things like that. Whereas a vector quantity is something that has 2 parts, both a direction and a length. Fancier way of saying length is magnitude. We'll use that interchangeably throughout this course. And so things that you might have seen in physics that are vector quantities are things like displacement, velocity, acceleration, force, and things like that. And so, yeah, we have scalar quantities, vector quantities. And so start talking about vectors. One type of vector we could think of is something called a displacement vector. So I could have this point A, I could have this point B, and then I could talk about the displacement vector from point A to point B and name it little vector AB with an arrow over it. And so with vectors, every time you draw one, you have the initial point or the tail, you have the ending point or the tip, and yeah, the displacement vector AB has its tail at A, its tip at B. And then you can name this vector U, for example. And so the convention I'm going to use is a little vector arrow like this above my vector quantities. Some people like to underline it. That's fine too. As you can see, when it's type written out, either in the textbook or in our notes, it'll be bold face like that. It's hard to do bold with handwriting, so that's why we either underline or put a little arrow on top. Obviously, I'm not really grading your written work ever, so you're not going to lose points if you don't use vector notation. But I really suggest that for this course, at least, you get into the habit of doing that. Later on, once you guys become professionals at vectors and things like that, when you get into upper level math courses and engineering, a lot of times they don't use different notation for vectors. They just sort of assume that you know what's a vector, what's a scalar based on the context. But for this course, there's enough scary new math concepts where your head is going to be spinning. The last thing you're going to want to do is confuse a scalar with a vector. And so I really recommend getting into the habit of doing something to distinguish scalar versus vector. So for me, I'll do my little arrows. You could do underline, whatever you prefer. All right, and so the thing to notice about a vector is it only depends on the direction and length. A vector doesn't really care where it's drawn. So for example, if I have other points, let's say point C and point D, that have the same relative position as points A and B do, then you could have a situation where we do the displacement vector CD, name that vector V, and it turns out that, yeah, in this case, if they have that same relative position, that vector U and vector V are the same. So you can have equal vectors that are drawn in different positions. It's the length, it's the direction that matters, not where you started. So something to keep in mind. Okay, and then one thing to mention is that there is a special vector called the zero vector. So yeah, I'll write it with 0 with a vector on it, but otherwise it's bold. And so the zero vector is the only vector that has 0 length, and it has no direction, or maybe it has all directions. You can kind of blow your mind wondering how you want to think about it. But basically, it's a vector where there's not a good answer to the question, what's the direction? So what are things we can do with vectors? So I guess there's two main things we could do with vectors. We could do something called vector addition, and we could do something called scalar multiplication. So if I have two vectors, let's say U and V, then I can do vector addition, which means I draw a vector U, and then I take the tail of V, put it on the tip of U, and I connect it like that, and then this vector down here is the vector U plus V. And so, yeah, that's vector addition. We have something referred to as the parallelogram law, which says that basically vector addition is commutative, that you can convince yourself with this picture here that whether I did vector U then vector V or vice versa, I get the same thing. So the parallelogram law is that U plus V, V plus U end up giving you the same thing. And so that's vector addition. And then scalar multiplication, the idea is you're combining a scalar and a vector, and basically you're stretching the vector while keeping the same length. So if I use vector U from above, then vector 2U is the same direction as U, but twice as long. Right? So maybe this has length of vector U. We'll use that notation in a second, but then this length will be twice the length of vector U. And so you don't have to, you can also compress it. So for example, I could do 1/2 U, where it's half as long, same direction. I could multiply by negative numbers. So, okay, let me try that a little bit better. Minus U is going to be the same exact vector, but opposite direction. And then I could do, like minus 1/4 U. And so that's the idea. The vector addition, you combine two vectors. So the input for vector addition is two vectors, and its output is a vector. For scalar multiplication, the input is one vector, one scalar, and its output is a vector. All right. And so I guess we need to talk about how we're actually going to do these operations. Like, we're not always just going to be drawing pictures like that. We need to actually do quantitative calculations. And so that requires us to talk about something called vector components. So if I have a vector A, let's start with vector A. You're going to draw it starting at the origin. And so, yeah, this O stands for origin. You're going to find then the tip of vector A and figure out the coordinates of that tip point. So let's call it A1, A2. Then we say that vector A has components A1, A2. So it's a little bit weird to wrap your head around. Most of the time you're going to want to distinguish coordinates of a point versus components of a vector. So when we use parentheses, that's coordinates of a point. And when you have these angled brackets, whatever you want to call it, that's components of a vector. So yeah, again, I'm not grading your written work, so you can use whatever notation you want, but there are many contexts in this class where you're going to want to separate these concepts and not get them confused. So I do encourage you to use parentheses when you're dealing with point coordinates, use then something else, these angled brackets, to deal with vector components. And so usually they're different. This is the one time when you have this correspondence. When you draw a vector starting at the origin, when vector starts at the origin, it's the only time you have this correspondence between a point and a vector. That otherwise, you're going to want to keep these two concepts separate. And so I just explained the 2D picture. The 3D picture is the same idea. You just have an ordered triple for your coordinates in 3D. Everything else is the same. And I think this next slide, I just caution you. Usually you want to distinguish between point versus vector. This is the one time where it's very hard to find a difference between these concepts, but usually when your vector isn't starting at the origin, these are very different concepts. All right, so anyway, now that we have components, we can actually deal with vector operations. So for points A and B, where we know the coordinates, to get the displacement vector, you just subtract the corresponding components. So again, AB, if you look at this formula, is minus BA. So for some things, it doesn't matter, AB versus BA. But to be really precise, be careful which order you do. So from A to B, you do the B coordinates minus the A coordinates. Okay. And then I don't know if I did this notation yet for vector length. I might have. But anyway, this is the notation we use for vector length. And so notice it's the same symbol we use for absolute value. So whether or not we're talking about absolute value or vector length depends on what's inside. So that's something that you have to identify from context. So if it's a vector inside, that's length of our vector A, or if it's a scalar inside, this is what I would call the absolute value of a scalar C. And so, turns out then, if you want to get the length of vector A, pretty clearly you could see from this picture, the length of vector A is the distance between the origin and the point with coordinates given by the components of A. And so if you remember yesterday, we talked about the distance formula, where you just subtract the corresponding coordinates, square those values, add them up, take the square root. And so because the origin is 0, 0, 0, you just get this equation for the length of a vector. Okay, and then how do our vector operations work with vector components? Basically, for for vector addition, you just add the corresponding components together. So first component of A plus the first component of B is the first component of A plus B. and so on and so forth. And then scalar multiplication, you distribute the scalar c to each component. All right, so that's how our operations work with components. And so now that you have that, you can pretty quickly determine all these properties. So A plus B is B plus A. That would be sort of commutativity is the math word for this type of property. And then if the operation doesn't care about how you add parentheses, then that's what we call associative. And then A plus 0, that sort of says that the 0 vector is the additive identity. It's the thing that when you add it to anything, nothing happens, and so on and so forth. Like, for example, this next one here, you could think of, well, this is like additive inverse. This is like distributive. Law for scalar multiplication and vector addition. Whereas this is also distributive law for scalar addition and scalar multiplication. And then I guess CDA, 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 that's sort of like an associativity between scalar multiplication with vectors and then number multiplication of scalars. And so, yeah, you could attach names to these. That's not super important. A lot of this stuff you're probably looking at, you're like, hey, Joe, that's like super obvious. Of course this stuff is true. And so, yeah, that's true in some sense. But some of the things we're going to talk about a few minutes later today aren't going to be so obvious or similar to the way numbers work. So anyway, yep, these are all properties that follow from the properties of number arithmetic. So what else to talk about in 12.2? Something called a unit vector. So unit vector is just a fancy way of saying it's any vector with length 1. And in certain applications, we need to find a unit vector with the same direction as some given vector A. So let's say I have this vector A. I don't know how long vector A is, but it's whatever. The length of vector A is its length. And I might need to get a vector with the same direction that has length 1. So I guess maybe in this case, A has length 2.5 or something like that. And the way I do that, to keep the same direction, remember our definition of scalar multiplication is that it scales or stretches or compresses your vector by some certain amount. And so basically to make vector A have length 1, we're going to take vector A and divide it by its length. And so that's what we call normalizing a vector. And yeah, that's something we're going to need to do occasionally. All right, so we haven't done any actual examples today so far. So let's say we want to do, we have some vector 2, -1, 3, and we want a unit vector in the opposite direction of 2, -1, 3. So yeah, whatever. We have 2, -1, 3. Essentially, yeah, for question A, we're looking for a unit vector, so length 1, in the opposite direction. Okay. So I guess we could use our vector length formula to figure out that vector A has length 4 plus 1 plus 3. I guess I could write out the first step. I'll usually skip this. 2 squared plus -1 squared plus 3 squared is, and I do not know how to square 3. Sorry about that. Yeah, it looks like our vector A has length square root of 14. So if I need to go in the opposite direction and get length 1, I accomplish opposite direction by multiplying by -1, and then I make it length 1 by dividing by its length. So opposite direction, remember with scalar multiplication, if you do a negative scalar, you flip the direction to exactly opposite. Okay. And then part B, we're interested in a vector of length 2 in the same direction as 2, -1, 3. And so now, I guess let's just look at part C as well. So I put these two here, which, you know, if you were being careless, the first time you thought about this, you might think that B and C are asking the same thing. I think actually a lot of people answer part C when they think they're answering part B. So let's just be careful here. So part B, I want my vector to be length 2. Part C, I want it to be twice as long as A is. So if you read carefully and think about it, you know, part B, that's what I'm looking for, a vector of length 2. Whereas part C, I'm asking for a vector twice as long as vector A is. So yeah, let's just call this vector A. And so yeah, based on our calculations from before, vector A has length 2√14, so that's what we want. So basically, for part C, you're just stretching A by a factor of 2, right? A vector with twice the length, same direction, that's just scalar multiplication 2 times your vector. Whereas part B is slightly more subtle. We have to do twice the unit vector in A's direction. So for part B, we're doing 2/√14 times 2, -1, 3. And so, yeah, of course, if you check the length of this, you'll get its length 2. Mission accomplished. So yeah, part B, part C seems similar. I think often we ask part B and people answer part C. So just be careful, think about it. All right. Last little topic from 12.2 is this idea of standard basis vectors. So I think this notation is used more often in physics, but we have these 3 special vectors, I, J, and K, that point along our X, Y, and Z axes respectively. So I points along the X axis, J points along the Y, K points along Z, and they're all length 1. So if you, whatever, looks like I have a little typo here. If you look at the components of these vectors, that's what they are. And so essentially it's just different notation for regular vectors. So I could write 2, 5, 1 with our angled bracket notation, or I could write that as 2i plus 5j plus k. And so the way the arithmetic works is that, yeah, 2i plus 5j plus k, that's 2 times 1, 0, 0 plus 5 times 0, 1, 0 plus 1 times 0, 0, 1. And so if you do that scalar multiplication and then that vector addition, you see that, yeah, that's the same thing. So it's up to you if you want to use component notation or IJK notation. For me, I really prefer component with the angled braces. I don't care for I, J, and K, but it really is up to you. So here's one example of some vector arithmetic with our standard notation. So the first thing I would do is distribute that 2 into 3, 1, and 2 to get the vector 6, 2, 4, and then add those components up to get 8, 7, 5. But you could also do it with IJK, in which case you're just kind of, it looks more like regular number or variable multiplication where, yeah, okay, that's 6i plus 2j plus 4k, and then you just kind of group like terms. So 2i plus 6i is 8i, and so on and so forth. So I don't know, physicists use the IJK. I don't really care for it. As I said before, I'm not going to ever be grading your written work, so I don't care which one you do. But I suppose you should be comfortable with both. That some questions will phrase using the component notation. Other questions we will phrase with IJK notation. So I think that's it from, that's it from 12.2. Any quick questions that hopefully seem pretty familiar? Nothing. Somebody here? Somebody missed the new code. What is the new code? Yeah, I'm not going to type it. All right, so I guess let's move on to something that probably a lot of you have seen before, but it's definitely a little bit trickier concept. So let's make sure we do it right. So the next section is something called the dot product, where you might be tempted to think that there's a such thing of vector multiplication. I would recommend not thinking of that, and I'll explain more as to why I feel that way in a few minutes. But yeah, we talked about vector addition, and then we talked about scalar multiplication. So scalar multiplication was, you have this vector A and you scalar multiply by vector C. So the input was scalar vector, output was vector. And so the dot product is going to be similar, except its input is two vectors and it spits out a scalar. So we're going to reserve this for dot product, this notation. I know that in other classes, or you might be used to using dot to designate regular number multiplication, but I'm not going to do that for this class. And I just, for the sake of keeping things straight, not confusing different ideas, I think it's a good idea to reserve this dot as meaning dot product. So yeah, that's the dot product. It combines two vectors and it spits out a scalar. And so what does it do? So intuitively, it takes into account the lengths of the vectors A and B, and it also takes into account how well the vectors line up. And so basically, anytime throughout this course where we're interested in how well vectors line up, we're going to measure that using the dot product. And so anyway, the formula for dot product is, if I have vector A and vector B, basically you multiply the corresponding components together and add this up. And so I've seen it so many times. People get careless and forget that the dot product is supposed to be a scalar. So I like to call this thing the half-ass dot product, where you sort of multiply the corresponding components but leave it as a vector, and that's bad. That, one of the most important things in this course is knowing when your answer is supposed to be a scalar versus when your answer is supposed to be a vector. And so don't give me a vector when I'm interested in a scalar. Okay, and so yeah, let's do a dot product real quick. It's not so bad. You just multiply the corresponding components and add it up. So 2 minus 5 plus 6 is, well, 3. And so, yeah, I don't even recommend writing something like that as an intermediate step, because what happens if you forget? You lose your train of thought and you leave that as your answer. I just will always write it out like this. I don't write any intermediate steps. But yeah, that's the dot product. All right, so we mentioned that the dot product measures how well the vectors line up. So how does it do that? So you can take a look in the textbook if you want. I'm not going to focus on it for this, but it turns out that the law of cosines tells you that the dot product is equal to the product of the lengths, so vector A length times vector B length, times cosine of the angle between them. So basically, theta is the angle between vector A and vector B. And so throughout this course, we're always going to measure theta to be between 0 and pi. So for example, if this is your situation here, we call this angle theta. We don't call this theta, which I'm trying to think. Does it matter? Huh. Is it ever going to pose? No, it's never going to pose an issue. So anyway, yeah, just keep that in mind. That's our convention for this. For the cross product, we always are going to do this convention as well. So we might as well just get used to it now. So yeah, it does make a difference when you think about the cross product. But anyway, that's our situation. And so yeah, now what you could do is you could think about when cosine theta is positive, negative, or 0. So remember, vector A length and vector B length, they're never negative. So first of all, let's assume that neither of these are equal to the 0 vector. If they are, then the dot product 0, no big deal. But yeah, if they're not the 0 vector, then the length of vector A is some positive number. And the length of vector B is some positive number. So basically, the dot product, whether it's positive or negative, is determined completely by this behavior of cosine. So now you just think about what's going on with cosine. Well, cosine is positive when theta is between 0 and pi over 2. It's negative when theta is between pi over 2 and pi, and it's equal to 0 when theta is equal to pi over 2. So that's what I've written down here, that basically I said that the dot product measures how well the vectors line up. So when you have a positive dot product, that means you have an acute angle, pretty good looking angle if you ask me. And if you're not laughing at that very clever joke, you're being obtuse. Yeah, telling jokes on this, I can't even, nobody laughs in person, but usually they groan. I can't hear the groans. That's rough. Anyway, so dot product positive means they make an acute angle. Dot product negative means they make an obtuse angle. And dot product 0 means that they're perpendicular, make a right angle. So if your picture looks like this, that A dot B is equal to 0. This up here would be a picture of positive dot product. This here would be a picture of negative dot product. So yeah, similar direction, perpendicular versus obtuse. And so yeah, whether it's positive, negative, or 0 tells you in general what their directions are relative to each other. But yeah, you could get more quantitative with it too. So for example, let's say I want to find the angle between these two vectors. So I know that the dot product of 2, negative 1, 3, and 1, 5, 2 is equal to the length of 2, negative 1, 3 times the length of 1, 5, 2 times cosine theta. So basically, I know everything on both sides of this equation except for theta. So let's calculate the dot product. Dot product is 2 minus 5 plus 3. We already did that on the other slide. The dot product is 3. And then the length, well, this is length 4 plus 1 plus 9, square root, and then square root of 1 plus 25 plus 4 times cosine theta. So theta is inverse cosine of 3 over the square root of 14 times the square root of 30. And so yeah, we don't use calculators on quiz. Well, we don't use calculators on exams, so that's how you'd have to leave your answer, not a special angle. But there we go. Okay, so similar to what we did with scalar multiplication and vector addition, we could take a look at some properties of the dot product. So it turns out that when you dot a vector with itself, you get the length of that vector squared. So why is that? Yeah, A dot A, you multiply the corresponding components. So you get A1 squared plus A2 squared plus A3 squared. But then remember, that's basically the length, but it's squared. So anyway, yeah, remember the length of vector A is the square root of A1 squared plus A2 squared plus A3 squared. Okay, and then the dot product is commutative. The dot product sort of distributes with vector addition. I guess it's associative with scalar multiplication. And so, yeah, if you have the dot product of two things being 0, you have that they're perpendicular. And so perpendicular, a synonym for that we'll use occasionally is the word orthogonal. It's just a different, it means the exact same thing as perpendicular, but just a different way of saying it. And so here you can kind of see, I told you a few minutes ago when we looked at this page for the other operations that you were probably all thinking like, oh yeah, that's obvious, whatever, why would you have to worry about that? But for this, okay, we could ask ourselves, you know, what if I do A dot B dot C? Is that the same as A dotted with B dotted with C? And so it turns out that this isn't even a question, because remember, the output of a dot product is a scalar. And the dot product is only defined to be between a scalar and a vector. So basically, as soon as I wrote down A dot B dot C, that's nonsense. That's not defined. And I think on the homework, we put a question where you have to take this kind of thing into account. So that's the other thing you're going to have to learn, that certain expressions that you can write down actually just don't make sense. Like, notice we haven't talked about, and we will never talk about, adding a scalar to a vector. So you can't just write something down and expect it to make sense. So there's rules, there's definitions going on behind the scenes, and yeah, dotting A dot B dot C doesn't make sense because B dot C is a scalar and the dot product is between two vectors. All right. So one of the things we could use dot products for is for this idea of projections. So in the past, I've noticed when teaching this that people, I think, are just frightened at the formulas, frightened at the idea, but it's actually a very basic concept that if I draw this simple case here, I'm pretty sure all of you will understand. So let's take a look at this vector 2, 3. And so 2 is what we would call the horizontal component. 3 would be the vertical component. So 2, like, what does that mean in the context of this picture? So let's draw this vector 2, 3. What 2 means is that this distance here is 2. And so we'll call 2 the horizontal component, or you could think about it as the amount that it points in the horizontal direction. Or the fancy way we could phrase this is the scalar projection of 2, 3 onto I. So remember, I is our standard basis vector that points in the direction of the x-axis. So scalar projection of 2, 3 onto I is 2. And so the notation we use for scalar projection is comp. So comp onto I of 2, 3 is 2. And so that's all we mean by scalar projection in this case. Okay. And so then we'll also talk about something called the vector projection, which, okay, the vector projection, you want to think about it as like the horizontal part of this vector. So let's draw that in. I think everyone's pretty comfortable with, yeah, the fact that this blue vector down here is 2, 0. So essentially the scalar projection is this length, whereas the vector projection is that vector. So the horizontal part of 2, 3 is the vector 2, 0. And that's what we call vector projection onto the horizontal direction. And we use this notation proj onto I of 2, 3 is 2, 0. So that's all we're trying to do. Except, what if we're not going onto the horizontal direction? What if I need to figure out this length of the part of B in A's direction? So this is getting out of hand. But it's really the same picture from this previous slide. Because our basis vectors are horizontal and vertical vectors, it's very easy to pick this off when I'm asking about the horizontal pieces of this. But when I rotate this picture, it's a little bit more complicated, but actually you can figure it out from playing SOHCAHTOA, that I already know theta is the angle between these vectors. I know that, yeah, if I draw this right triangle, this is the adjacent side of theta, so it's hypotenuse times cosine theta. And, well, cosine theta, oh yeah, we'll plug that in a second, but that's what the comp onto A of B is that adjacent side in that triangle here. And, okay, yeah, so length B cosine theta. Remember, cosine theta showed up in that equation for the dot product. Remember, dot product was product of lengths times cosine theta. So cosine theta is dot product divided by product of lengths. And what do you know? The length of B cancels out, and so you're left with this formula here. And if you go back to our discussion earlier, so let me write it over here, that the vector of length 2 in A's direction was 2A over the length of A. So the vector projection here is a vector of length comp onto A of B in A's direction. That the relationship between this length and this vector is, yeah, it's just a vector of that length in the direction of vector A. So you can do the same kind of thing. This is the desired length times a unit vector in the direction you want. Desired length times unit vector in the direction you want. And so anyway, it's the dot product over the length A squared times vector A. So you can figure this out. I know that you guys don't like doing that, and that's fine. Memorize these formulas. And so the way I remember it is that this is, all this stuff here is B onto A. So B onto A kind of suggests that B is above A, right? So A is in the subscript. So B is onto A corresponds to A being in the subscript. And then it corresponds to, once you get to these formulas over here, it's the length of vector A that's in the denominator. So I think for people that memorize these equations, all there is to it afterwards is to figure out which one's which, because A onto B onto A is different. And so I like to remember it by saying, okay, B onto A. A is in the subscript. Length of A is in the denominator for these formulas here. And so for the sake of time, I'm not going to do an example. I'm sure you'll have practice on the homework. Dom can go over that tomorrow, or Stephen on Thursday. But yeah, that's the dot product. We could pause again if, see if there's any quick questions. It's seeming a little familiar. Dot products are important in physics. Yeah, so I think you guys have solved, you might not have called it vector projections, but you know, if you have an object on a ramp and you're trying to figure out if gravity is going to cause it to move, you have to figure out how much the force of gravity points along the ramp to figure out if it overcomes the friction force. So yeah, anytime you need to know how much something points in something else direction, that's this idea of projections, and it's tied to the idea of dot products. But I guess let's keep going. All right, so cross product. So again, it's not going to be something we want to think of as multiplication. I'll get to that in a few minutes, but it's similar to the dot product in that it takes two vectors as its input, but then it's different from the dot product based on the fact that it spits out a vector as opposed to spitting out a scalar. So that's the key difference. So out of all our operations, keep straight vector addition versus scalar multiplication versus dot product versus cross product. And so cross product, we're going to use the little times notation you might have used earlier in your schooling. But again, I'm not going to use that for anything other than cross product. I recommend you guys do the same. All right, so what's the point of the cross product? So the point of the dot product was it tells you how well the vectors line up, remember? So I'd like to think about the point of the cross product as being it's a way to get a new vector perpendicular to both A and B. So the picture you want to have in mind is that I have some vector A, I have some vector B, and I want to figure out something that's perpendicular to both A and B. So that's how you could draw that situation. And it turns out that the cross product is going to accomplish that for us. So starting next week, when we start messing around with equations of planes, we're going to need a vector perpendicular to a given direction, two given directions. Okay. So the formula for the cross product is a big, gigantic, scary mess. So A1, A2, A3 cross B1, B2, B3 looks like that. So do I suggest you memorize that? No. So an easy way to remember this formula is to use this idea of a 3x3 determinant. So I guess over off to the side, I will refresh your memory for what a 2x2 determinant is. So if I have a 2x2 matrix or array of numbers, it doesn't matter what you call it, but essentially what you do is you multiply the diagonal elements from each other and then subtract. And so you do it in the order top left times bottom right minus BC. And no, it is not a typo. No, it's, yeah, we'll talk about that. That's the thing everybody screws up. So don't feel bad. And so anyway, that's a 2x2 determinant. And so the way you do a 3x3 determinant is as follows. So 3x3 determinant. There's so many ways you could do it. If you take Math 220, you're going to learn a lot more of these. But for us, it's going to be nice to go, we'll just always go across the first row. And so when you're doing a 3 by 3 determinant, you go across, let's say, the first row, and you alternate signs. So let's use a color for this. Alternate signs means that I do plus, minus, plus. And what I've done here is this here is what I have left when I delete the row and column I is in. So when you go across, you start with I, and then you delete the row and column that I is in, and you're left with A2, A3, B2, B3. And so essentially what we're doing is recursively defining a 3 by 3 determinant in terms of 2 by 2 determinants. So you get I times this stuff. Then we alternate signs. So it turns out, yeah, you have to put this minus, but then for J, you do J times, you delete the row and column that J is in, so A1, A3, B1, B3, and then plus K times A1, A2, B1, B2. And so this is I times A2, B3 minus A3, B2 minus J times A1, B3 minus A3, B1 plus K times A1, B2 minus A2, B1. And so now you see that's not a typo. This minus here causes that to get flipped, that A3, B1 minus A1, B3. And so that's the one little sticking point that most common mistake for this part of this course. And sadly enough, it doesn't go away. I'm still going to see that mistake on the final exam. So watch out for it. If you don't do it, then you won't get something perpendicular. So yeah, as practice, let's do 2, 3, 1 cross negative 2, 4, 1, negative 1, and confirm that it's perpendicular to the input vector. So, okay. I put my first vector in the second row and my second vector in the third row. And so throughout the rest of this course, I'm not going to really write out these steps. It's not something you're going to learn by watching me do. Whatever little shorthand you like to do for this is fine with me. So anyway, I delete the row and column that I is in. So if I delete the row and column that I is in, I'm left with 3, 1, 4, minus 1. Then I have my minus J times 2, 1, negative 2, negative 1. 1 sec. All right, recording back on. So yeah, we delete the row and column that J is in. So we're left with 2, 1, negative 2, negative 1. Oh, and did I really do this? Yeah, it's going to be 0. But anyway, for the middle component, that's fine. Plus K times, I delete the row and column K is in, so 2, 3, negative 2, 4. So yeah, I delete the row and column that K is in. And there we go. And so I get, at this stage, I usually just write it in my brackets. So negative 3 minus 4 is negative 7. Negative 2 minus negative 2 is 0. So yeah, I wish I didn't do that because now the delicate one that everyone screws up ended up being 0, but that's not usually the case. And then for K, I get 8 minus negative 6 is 14. And so then, okay, is -7, 0, 14, perpendicular to 2, 3, 1, well, now we have to think. We learned about this in the previous section. How do I tell when two vectors are perpendicular? When their dot product is 0. So that's something we're going to be using throughout this course, so get used to it. To check for perpendicular vectors, I take the dot product. It looks like I get -14 plus 0 plus 14, which is 0, so yes. Dot product 0. I'm writing too close to my buttons. Dot product 0 means perpendicular vectors. And I'm not going to do it, but if you dotted it with -2, 4, -1, you would also, of course, get 0 for the dot product. All right. But yeah, without this minus, this wouldn't be true in general. That, let's see here. Let's check this based on this formula on the next page. A dotted with A cross B is going to end up being A1 times A2B3 minus A3B2 plus A2 times A3B1 minus A1B3 plus A3 times A1B2 minus A2B1, and you'll see that that's 0. And it's actually important that this is the way it is, because here we go, A2, A3, B1 with a plus is going to be minus A2, A3, B1 right there. So write it out, make sure you're convinced, but people always wonder, oh, this minus sign, that's so annoying. Does it have to be there? Well, yeah, the determinant does very special things for us, and without that minus, it wouldn't work out. Okay, so we have a similar formula for cross product in terms of this angle theta. So remember, the dot product was A dot B is length A, length B, cosine theta. So it turns out the length of A cross B, so again, because A cross B is a vector. So, you know, if I got rid of these vector lengths here, this wouldn't make sense. I can't have a scalar equaling a vector. But if I take the length of vector A cross B, it's the product of the lengths times sine theta. And so essentially what this tells us then is that the area of the parallelogram formed by these two vectors, vector A and vector B, if you do the SOHCAHTOA game, it's base times height, and height is equal to, well, the base is vector A length, and then the height, you do this little right triangle and get that the height is length of vector B times sine theta, and that's precisely what you have to believe, that cosine formula, which means you have to believe the law of cosines. But it turns out that, yeah, the length of the cross product is the area of this parallelogram. And if you just, instead of the parallelogram, if you were interested in just the triangle, then that's going to be half of the parallelogram area. All right. So let's do an example. To find the area of the triangle with these vertices. So bad thing to do is to start doing something like 2, 1, 4 cross 3, 3, 3. That is not what we want to do, because we don't want to cross points. We don't take the cross product of points. And so this is one of those situations where, yeah, sure, it's confusing that a point has 3 coordinates, a vector has 3 components, but we don't want to interchange or confuse the idea of point and vector. So 214333, you're allowed to cross those vectors, but that's actually not relevant for this question. So let's draw a little picture. And so here's a good example of a picture that I'm not really concerned with the accuracy of this perspective. But okay, let's pretend I'm not going to draw my X, Y, and Z axes, so who knows, but I can go to some perspective where this is the general idea of what I see. Okay, so this is the triangle that I'm concerned with. Okay, so if we go to this picture here, we have to cross the vectors that make up, that point along the sides of this triangle. So the vector 214 as a vector starts at the origin and stops at the point 214. And so you see that's actually not relevant for this question, this triangle. That when you take point coordinates and turn them into vector components, you're getting the vector that starts at the origin and stops at the point. But that's not a vector we care about for this triangle. So instead, what we need to do is to get displacement vectors along the sides of this triangle. So it's actually PQ and PR that I'm going to want to take the cross product of. The answer to this is 1/2 the length of PQ cross PR. So I have to get this displacement vector PQ is 1, 2, -1. I have to get PR, which is going to be 3, 0, -2. So that's what I'm going to do. I need to do IJK 3, or let's do 1, 2, -1, and 3, 0, -2. And yeah, let's get that cross product. That's going to be -4 minus 0. -3 minus -2 is -1. And then -6. So again, I'm going a little fast. And now I take the length of this. So the length of -4, -1, -6 is square root of 16 plus 36. So what is this? 53 plus 1? Yeah. And so my final answer is square root of 53 over 2. So great question. I knew this was going to be asked. So many times in this course, you're going to have choices. And as long as you're doing something correctly, it should give you the same thing. So for example, it's not so hard to convince yourself that what's so special about P, Q, and R? What if I instead did, like which one's which isn't special? What if I instead did something like this? Or if I just did PQ and RQ? Or QP and RQ? That essentially, as long as you're using two different displacement vectors, you will get the same answer. So, you could do 1/2 length of PQ cross QR, like you said, or you could do 1/2 length of QP cross QR or RQ, whatever. Essentially, yeah, you could do those and you'll get the same thing. And I think Dom will bring this up tomorrow in recitation. He'll sort of try to explain this. But yeah, if you're doing correct choices, you will get the same answer. There is a little magic, though, behind the scenes. And so that's why I think I'll save it for a discussion in recitation tomorrow. But yeah, great question. And yeah, you could use that as well. All right, so let's keep talking about the cross product. Yeah, some of why it ends up being true, it's going to follow from things we're about to discuss. Okay, so if you look at this formula for A cross B, if I switched the A's and the B's, I'd be multiplying the whole thing by -1 because of these minuses. So it's not too hard to see from the formula that A cross B and B cross A are exactly opposites of each other. And so the reason for that is that graphically you want to think of the cross product as following the right-hand rule. So the idea with the right-hand rule is you go through A, then B, by sweeping out less than 180 degrees, or pi, because we're adults, we use radians. So when you go through A, then B, you don't take the long way, you take the short way. And so if your fingers go through A, then B, like that, then your right-hand thumb is pointing up, so that's A cross B. If instead you were to do B cross A, then you would do your fingers through A, then B, and you'd be pointing down. So yeah, B cross A points down. And so it turns out you could think of this as part of the definition of the cross product, or maybe it's a consequence of the formula, but it turns out that if you said that, okay, I want to define this cross product so that I have that perpendicular property, I have the length property, then there's only two choices for what the cross product could be, and we've made the choice that the cross product will be the one that then does the right-hand rule. So that's that. And so now we can talk about some properties of the cross product. So yeah, it's not commutative. It's, I guess, what you would call anti-commutative. With numbers, 2 times 3, 3 times 2 are the same thing. But with cross product, B cross A cross B are opposites. So it's not quite like multiplication. This is also pretty strange too, right? With numbers, is it true that any number squared is 0? No. But any vector cross itself is the 0 vector. Because if you look at that formula, if I do A2, A3 minus A3, A2, right? If I'm just all the A's and B's, they're all A's, so you get 0. And you can figure out some other things. It does have distributive with vector addition and things like that. But then, okay, if you go back to the formula where the length of the cross product is the product of the lengths times sine theta, think about the behavior of sine. Sine theta is 0 when either theta is 0 or theta is pi. So theta 0 is same direction. Theta equals pi is exact opposite directions. And so some contexts you might want to distinguish this between parallel and anti-parallel, but technically we're going to define parallel to be either of these. And so that's our fancy symbol for parallel. So remember, the cross product is 0 when your vectors are perpendicular. The cross product is the zero vector when the vectors are parallel. And you could also think about parallel vectors as coming from the idea of scalar multiplication, that scalar multiplication either has same direction or opposite direction. So that's our characterization of parallel vectors. Okay, and then it's also handy for cross product to understand its behavior on the standard basis vectors. So we already said that any vector cross itself is zero. So I cross I, j cross j, k cross k are all the zero vector. And then, okay, what happens if you cross different vectors? So you want to think about this like sort of alphabetical order where k cycles back to I. So if you're going with these arrows and not skipping anything, I cross j is k. Okay? Whereas j cross k is I. And k cross I is j. But if you go in reverse, if you do j cross I, you're going against the arrows, so you pick up a minus sign, and so on and so forth. So here I'm just going to put a little quick example. It's not... no, this will be at the end of the lecture. I forgot. Okay. So let's keep on going, and then I'll show you something neat at the end. Okay, so finally, we have this thing. We can combine the dot product and the cross product into something called the scalar triple product. So the scalar triple product, the input is three vectors, hence the name triple, and it spits out a scalar, hence the name scalar triple product. And so basically, we define it as being A dot B cross C. So remember earlier I said you have to be careful. Do these expressions make sense? And well, B cross C, that spits out a vector. And yeah, the dot product of a vector and a vector is a scalar. So yeah, this makes sense. You can dot two vectors together. And so you can do the cross product first and then do the dot product, but you could do this as a single 3x3 determinant where instead of ijk in the top row, you use our first vector A. So yeah, A dot B cross C, you could do that determinant. Turns out that, yeah, you could be a little cyclical with this, that ABC, BCA, CAB give you the same thing. Again, be careful if you switch any of these cross product orders, you're multiplying by -1. I didn't want to do that. So yeah, this, sorry, you pick up a -1 factor if you do A dot C cross B. It turns out then we had that geometrical interpretation for parallelogram area in terms of the cross product. Well, it turns out that the volume of the parallelepiped, so parallelepiped, you take your three vectors, A, B, and C, and you make sort of the three-dimensional analog of a parallelogram. And so it turns out that the volume of this is the absolute value of the scalar triple product. And so then you ask yourself, when would this scalar triple product be zero? What would that mean as far as the parallelepiped volume? So you can have any two vectors always live in a plane, but three vectors may or may not. So if you have three vectors, A, B, and C, that point along the same plane, then you have zero as this parallelepiped volume. And then, yeah, to tie it all together, parallel vectors are characterized by zero dot product. Perpendicular vectors are, perpendicular vectors are zero dot product. Parallel is zero cross product. coplanar is 0 scalar triple product. That's a lot of information. I think a lot of this you've seen, but make sure you get going on the WebAssign. We've got 2 sessions with Dom, 1 session with Steven, so that should be good. But the last thing I want to leave you with is you might be tempted to think about either of these, dot product or cross product, as vector multiplication, but I don't really think that we should. So what are some properties of number multiplication that we like? So for example, when you multiply a number, it spits out a number. So I'm allowed to do something like A times B times C, that's okay to do. Commutative means, of course, that like A times B is B times A, right? 2 times 3, 3 times 2, same thing. Associative, A times BC is A times B, then times C. That doesn't matter which 2 you multiply together first, you're going to get the same thing. And then finally, we have something called the zero product property. So what's the deal with 0? What's so special about 0? The only way you could have 2 numbers multiplied to be 0 is if one of them is 0. So these are some properties of number multiplication that are not true for these dot and cross products. So that's why I don't like thinking about these as vector multiplication. So dot product doesn't give a vector back. So remember, I mentioned that you can't dot product 3 vectors together. That just doesn't work, because when you do the dot product, it spits out a scalar. So that's no good. And then the zero product property fails. So for example, let's take the vector 1, 1, 1 dotted with 1, negative 2, 1. Well, that's 1 minus 2 plus 1, which is 0, which, like, neither of these vectors are the 0 vector. It does turn out that 1, 1, 1 and 1, negative 2, 1 apparently are perpendicular, but we don't have this property like we had for numbers, that if the 2 numbers multiplied to 0, at least one of them has to be 0. Well, simply not true for dot products. So what's not true about cross products that number multiplication has? Well, A cross B is minus B cross A. That's the anti-commutative property. Not associative either. So this, let's play around with. I cross K. So with numbers, you don't have to pay attention at all to parentheses, right? 2 times 3 times 4, no matter how you swing it, is 24. But with cross products, that's not the case. So I cross K, if you look back a few slides, we did the behavior on the standard basis vectors. I cross K is minus J. And then I cross minus J ends up being minus K. And then if I do I cross I first, I get the 0 vector. Because remember, anything cross itself is the 0 vector, and then 0 vector cross anything ends up being the 0 vector, so that's not the same. You know, with numbers, everything's great. 2 times 3 times 4 is 2 times 3, then times 4, who cares? This cross product idea is bizarre. And even more bizarre, I mentioned, with numbers, you square a non-zero number, you don't get 0. But any vector cross itself is the 0 vector. So hopefully that convinces you a little bit. You have to be careful with things. That I'd say scalar multiplication and vector addition, those are the nice ones. That basically they're exactly like number multiplication and number addition in some sense. So yeah, all those beautiful properties that you would assume to be true are true for that, but now you have to be careful that dot product, you can't dot three things together. That doesn't make sense. You don't have the zero product property. For cross product, you have this scary non-associativity. So be careful. No, that was a quick, but yeah, give the homework a shot. Post on Piazza for requests for Dom or Steven for either of those 3 sessions coming up the next few days. But yeah, that's about all I had for today. That was a lot of information. Do you guys have any questions? No questions? Well, I'll stop the recording, but wait for you guys to trickle out.